Let's go through another example of using the simplex method to solve a standard maximization problem in linear programming. And this time we'll set it up via a story problem. So in this problem, we imagine that as a small business owner, we're planning to buy some radio spots in order to advertise our business. And we have a choice of buying either regular spots or peak time spots. So those peak time spots might be during rush hour, for example, when more people are in their cars listening to the radio. And so they cost more, but they'll also get more customers. So the local radio station we're going to advertise on will allow us to buy up to 100 ads in a given week. They don't want more than that. Maybe they want to make sure there's a variety of different ads on their station so as not to overwhelm customers or listeners. And you have a budget of $20,000 to spend on these radio spots. Now, each regular spot costs $100 and will result in 2 new customers for our business. This is an estimate. And then each peak time spot costs more, costs $500, and it will result in 5 new customers. So the question is, given the constraints on the number of ads we can buy and the amount of money we have to spend, how many of each type of spot should you buy to maximize the number of new customers? Now, notice that if there were no constraint on the number of ads, this would be an easy choice. We could spend all of our money on the cheaper ads and get a greater return for each dollar. But because of the constraint on the number of ads, it turns out we really want to be careful about answering this question and use a linear programming approach to answer it. The unknowns in this question are how many regular spots to buy and how many peak time spots to buy. So let's introduce variables to represent the unknowns and write down what those variables will mean to us. So I'm going to let x be the number of regular time spots, and I'll let y be the number of peak time spots. Using those symbols, we'll begin to translate the values that are given in the description of this story problem. Now, we want to maximize the number of customers, so we need to look through the information described here to figure out what that function is that we're maximizing. Well, we get 2 new customers for each of the X regular spots and 5 new customers for each of the Y peak time spots. So if we combine those, we can write down our objective function we're hoping to maximize 2 times the number of regular spots plus 5 times the number of peak time spots. And then looking back through the rest of the description, we can write down the constraints. First of all, the total number of spots we can purchase is less than or equal to 100 because that's the most the radio station will let us purchase. And because we only have $20,000 to spend on advertising, we multiply the number of regular spots by $100 each and the number of peak time spots by $500 each, and that total has to be less than or equal to the $20,000 we had to spend. And then we also remember that we cannot buy a negative number of ads. So X and Y both have to be greater than or equal to 0. And looking over everything now, we see this is a standard maximization problem, so we will be able to apply the simplex method. We start by introducing the slack variables that allow us to change each of the constraint inequalities into equations. And we write down the objective function in the form of an equation with all the variables on the same side of the equation as our plus f. Now with these 3 equations, we can write down the corresponding augmented matrix representing that system of equations. And we want to identify the pivot, so we look for the largest negative number in the bottom row. That occurs in the second column. Therefore, the second column is our pivot column. And then we look at our test ratios. 100 divided by 1 gives us 100. 20,000 divided by 500 gives us 40. And 40 is smaller than 100, therefore the second row will be our pivot row. The entry in the pivot column and pivot row, second column, second row, is that 500 we see. That's the pivot, and we can begin pivoting our matrix from there. The first thing we'll do to make the other operations easier is to change the pivot into a 1. So I do that by dividing the entire pivot row by the number 500. And we can see that this is the result of that division. Next, I want to make the other values in the pivot column equal to 0. Using the pivot to make this 1 into a 0, I can subtract the pivot, so I'll subtract the pivot row from the first row. And to make this negative 5 into a 0, I can multiply the pivot by 5 and then add it. So I'll add 5 times the pivot row to the third row. So going through it very carefully, if I subtract the pivot row from the first row, I have 1 minus 1/5 gives me this 4/5. 1 minus 1 gives me 0. 1 minus 0 gives me 1. 0 minus 1 over 500 gives me negative 1 over 500. 0 minus 0 gives me 0. And 100 minus 40 gives me 60. The pivot row itself doesn't change, so we just recopy it. And then for the final row, we have to remember that as we're adding, we're multiplying the pivot row by 5. So 5 times 1/5 is 1. Add that to negative 2. 1 plus negative 2 is negative 1. 5 times 1 is 5. Add that to negative 5. We get 0. And the same operations apply across the bottom row. Now we've completed a pivoting of the matrix, but we see a negative number still in the bottom row. So we have to go through a new cycle of pivoting, which means finding a new pivot to begin with. The only column with a negative number in the bottom row is the first column, so it must be the pivot column. And then we look at test ratios. 60 divided by 4/5 is 75. 40 divided by 1/5 is 200. The smaller of those is 75, so the first row is our pivot row. Our pivot is in the first column, first row. We put a box around it to help us keep track. And we're going to use that pivot to make the other entries into zeros. This time, I'm going to make the calculations later easier for myself by first changing the pivot into a 1. So to change 4/5 into 1, I can multiply by its reciprocal 5/4. I do that to the entire first row, and that produces this new first row. And then the following operations will be to make this into a 0 by subtracting a 5th, so I have to subtract 1/5 of the pivot row. And to make this into a 0 by adding the pivot, so I just add the pivot row to the third row. And the matrix we see below is the result of those operations. Now there are no negative numbers left in the bottom row, which means we're completely finished pivoting this matrix, and all we have to do is evaluate the meaning of this matrix. So we can make that a little bit easier for ourselves by adding labels to the columns to remind us what variables each column corresponds to. We identify the active variables. Those are the variables that come from columns where there's only one entry that's not 0. The other columns give us the inactive variables. And remember, as soon as we know a variable is inactive, we know that its value is 0 in the final answer. We can use those values to plug into the equations we get from reading the rows of this matrix. The first row corresponds to the equation 1x plus 0y plus 5/4 s minus 1 over 400t plus 0f equals 75. Leaving out the variables that have coefficients of 0, we get this equation. Plugging in 0 for each of the inactive variables, we immediately see that x is 75. Now if we do the same work on the second row, we get an equation for which we can plug in the zeros for inactive variables and obtain a value for y. And from the third row, we get another equation. We can plug in zeros for the inactive variables and get a value for f. So from this, we can see that we will obtain a maximum value of f, and remember f represented the number of new customers we were getting. We can get the maximum value of 275 new customers if x is 75 and y is 25, but the answer to a word problem should be a word answer, so expressing that in words, x was the number of regular radio spots, so we want 75 regular radio spots and 25 peak time spots. Now, let's also mention a little bit about the slack variables. The slack variables tell us how much is left of a resource. So for example, the variable s in this problem was part of the equation that came from the constraint on the number of ads we could buy. So x is the number of regular ads, y is the number of peak time ads, s would represent the number of additional ads we could have bought before hitting our maximum of 100. Because we ended up with a value for s equals 0, x plus y actually equals 100 in our final answer, which means we bought all the ads we possibly could. Similarly, since t is 0, and t was part of the equation representing the total amount of money spent, the fact that t is 0 tells us there wasn't any money left over at the end. Now you can imagine a different example where we end up with different values for s and t. Maybe they're not inactive at the end. Maybe they end up being active variables. So those values would tell you something about what resources you have left over. In the context of a problem like the one we're doing now, if we had set it up similarly, but different initial values resulted in a different solution, we might have seen s is 10 and t is 50, and we'd be able to interpret that as telling us that we could have bought up to 10 more ads, but we only had $50 left. So again, this is not related to the problem we solved just now. This is a hypothetical different problem just to illustrate what values for the slack variables can tell you at the end of applying the simplex method.